Okay, so last time we got into chapter 4, which is about atoms, obviously, and we talked about some important sort of experiments that led to better understanding of the structure of the atom. Remember some of the important things that you do need to know, Dalton and his atomic theory. Remember that parts of Dalton's atomic theory are not correct. For example, all atoms of the same element are identical to each other. Again, as we talked about, the existence of isotopes, which are the same element but have different masses, kind of disproves that. Remember as well, sort of the early work into looking at electrons, protons, and neutrons all really revolved around the idea of sort of opposites attract and the use of a lot of sort of radioactive, say, particles, and the ability to use that electrostatic attraction to really see what's going on with particles that have charges. So as we talked about, you can use something like an electrical field and, it will have an effect on particles that have charges. So something like negatively charged would be bending towards the positive side. Something with a positive charge would be bent towards the negative side of the electrical field. And obviously something with no charge would just really sail sort of right through. So one of the earliest sort of advancements in terms of the electron was done by Thomson. He used the cathode ray tube to really explore the nature of the electron. And he was able to figure out the charge to mass of an electron. And that was followed up by really the next kind of important experiment in terms of electrons, which was Millikan. He did that oil drop experiment. That oil drop experiment, basically, he shot oil droplets into a chamber. The droplets would go through sort of an electrical field, and as they would fall, they would gain a sort of charge as they would fall. And he was able to really sort of adjust the electrical field in such a way that it allowed sort of the oil droplets to be suspended. From that, he was able to figure out the not mass, the charge on an electron. And using really both of these sort of values here, the mass of an electron was able to really be determined. And that's something like 9.09 times 10 to the minus 28 grams. This led to sort of the idea that, as we talked about, that they really did believe that the atom was neutral. So obviously, if it contained these negatively charged electrons, it had to have something that was positively charged. And that came in the bout of one of the first models of the atom, which was the plum pudding model. And that basically is a sphere of positive charge. So we had all this positive charge spread out. We had these electrons embedded inside. And they felt that most of the mass of the atom was these electrons. And this was sort of the accepted model of the atom, also done by Thomson, different Thomson, but until really the next major sort of experiment came about, and that was our friend Rutherford. And Rutherford did the gold foil experiment. And he shot alpha particles, which are positively radioactive particles at pieces of gold and other metals. And what he expected to happen as a result of this sort of model of the atom was, because he was shooting these positively charged particles going through this kind of positive pudding, if you will, he did expect them to punch through but be deflected. And what he actually saw was kind of surprising. He saw that most of them went through pretty much undeflected. And every now and then, they did see some of these alpha particles get deflected at really large angles. So what that meant was they really had to revisit this model of the atom and sort of throw out the plum pudding model and come up with sort of a new model of the atom, which he said was mostly empty space. And that accounted for why most of the alpha particles sail through with no problem. It did have a dense positive core, which is known as the nucleus. That's what accounted for those alpha particles that banged off at really large angles because it hit something very, very positively charged. Where later experiments found that in the nucleus, that's where we have our protons, which are positively charged, and our neutrons, which are no charge. Like 1930s, that was discovered. He also said that most of the mass of the atom was actually the nucleus. And that makes sense because, as we later talked about, both a proton and a neutron is about 1,800 or so times heavier than any electron kind of flying around. So they're both in the nucleus and they're way heavier than an electron. So that makes sense that most of the mass of the atom is actually the nucleus. Out of all three of those particles, we also talked about it is the neutron that just barely edges out the proton in terms of being the heaviest of all three of them. Remember as well, there is an attraction between the electrons, which are flying around randomly about the nucleus, and the nucleus, which is positively charged as well. We then got into atomic number. The atomic number is the number of protons in an atom. It is the number that you can see on top of the symbol on the periodic table. The mass number is the number of protons plus the number of neutrons. Remember that the mass number is not found on the periodic table. So again, the mass number is not the number, put an X, not the number there below the symbol. Remember that when you calculate atomic number, mass number, number of protons, electrons, neutrons, they all has to be positive whole numbers. And again, most of those numbers on the periodic table on the bottom are pretty much decimal numbers. So that's a good way to remember it. How do you get to your neutrons? Well, you get your number of neutrons by taking the mass number and you subtract the atomic number from it. And remember that we can write sort of symbols for isotopes, which have different neutrons, by taking the symbol top left is the mass number, bottom left is the atomic number. So that's a very common way that we can write sort of the symbol for the isotope with their mass number and atomic number. So essentially, if you have it written like that, you take the top number minus the bottom number, and that'll give you your number of neutrons. Everybody, as we talked about, has protons, electrons, and neutrons, except for hydrogen. Hydrogen only has a proton and an electron. It does not have a neutron, but everybody else has all three of those sort of particles. Any questions on any of that stuff there we talked about last time? Okay, then I think we kind of left off here at this example, I think. So why don't you take a moment for each of these and figure out how many protons, electrons, and neutrons each of these guys will have. Okay, so let's take a look and see. Once again, first off, when we do see the symbol written like this, one thing that we know for sure is there's no charge. Otherwise, there would be something obviously written up there top right. So we don't see any pluses or minuses. So we can assume obviously that this is a neutral. Remember again, top number here is our mass number, which again is our protons plus our neutrons. Bottom number here is our atomic number, which is our protons. So right off the bat, we do know just from the bottom number there, the number of protons in this case is 27. We also know that it is neutral, which means in order to balance it out, we would need the exact same number of electrons. So it should have 27 electrons. That gives us really an overall charge of 0. Since out of those three particles, the protons are positive, the electrons are negative, and the neutrons have no charge. So we got to have an equal number of electrons if we have no charge. Our number of neutrons here are going to take our mass number, which is 60, minus our atomic number, which is 27, and that's going to give us 33 neutrons. Questions on that there? Coming to the next one, same deal, no charge. So we'll start with the bottom number, which is our protons. So again, that means that we do have 17 protons happening. Once again, since it is neutral, we need an equal number of negative charges from our electrons, again, to give us basically no charge overall. And then lastly here, our neutron's going to be 37 minus 17. I'll give it a go without a calculator. 20 here, number of neutrons. Any questions on any of those though? All right, lastly, U, which is uranium, once again, has no charge. We'll start with the bottom there, which is 92, gives in our protons, which is our atomic number. Again, no charge means we will have an equal number of negatively charged electrons, again, to give us no charge. And our neutrons will be Mass number 238 minus 92 feels like a lot. Of 146 we'll go with. So, any question on any of those numbers? Again, all whole numbers, all the information needed to figure out protons, electrons, and neutrons will be given to you in this problem. Again, the only thing from the periodic table, atomic number, right? Any questions on that? All right, let's try a few here. Why don't you write the symbol that has the atomic number and mass number in it for these isotopes? Let's see what you come up with. Okay, so let's take a look. So once again, here we have krypton, has 48 neutrons. So we do want to probably go to the periodic table, find krypton, which is Kr. We can get some important information from that. If we look on the periodic table right above it, it's going to say 36. That is our, again, atomic number. So that's going to allow us to know we're going to go with Kr, and we do put the atomic number there on the bottom left. And our mass number, which is, again, our number of protons plus neutrons. We already know that our atomic number is 36, which is that's how many protons there are. 48 neutrons they gave us in the problem will give us 84 for our mass number. So we'll look something like that there. Questions on that? Next is nitrogen. So again, periodic table, your friend here, you go to the periodic table, you'll find nitrogen. It'll look something like that with a 7 up on top. That means that we're going to put the 7 on the bottom, which is the atomic number. Our mass number will be our 7 plus 6 will equal our mass number, which is our protons and our neutrons. And that is 13, it looks like here. And we'll have something like that. Lastly here, we want iron. Iron is actually Fe on the periodic table, number 26. In this case, they actually gave us the mass number. So that makes it pretty easy to write the symbol. 56 on top, mass number. 26 on the bottom there for our atomic number. It also wants the number of protons, electrons, and neutrons. So once again here, number of protons should be 26 in this case. It is neutral. And we assume that it's neutral because it doesn't mention anything about an ion or anything like that. And we would have an equal number of electrons. And our number of neutrons in this case would be 56 minus 26, which would give us 30 in this case. Any questions on any of those? Writing symbols, mass numbers, atomic numbers, protons, electrons, and neutrons. So what would happen if we actually did have something that had a charge? So if we had something that had a charge, I'll steal some of this here. Those again are what are referred to as ions. These are things with charges. There are cations, which are positively charged, and there are anions, which are negatively charged. So if we take maybe these couple examples we got here, we're gonna get rid of some of these here, get a little room. So if we take, let's just say the nitrogen here to start with, and I'll put back what I erased there. Protons was 7, electrons was 7 as well. And our number of neutrons in this case, 13 minus 7, which is 6. So let's just say we did have a nitrogen here that had a -3 charge, and still the same sort of guys here. So a couple of things when we look at it, first off, it still has 7 protons because the atomic number is still 7. So the number of protons here is going to still be 7. It will still actually have the same number of neutrons as it is 13 minus 7, which would be 6 in this case. So that leaves us only the electrons that are going to change here with the charge. And by the way, why would the protons not change with the charge? If I change the protons, what happens? Yeah, it's no longer nitrogen, right? So the protons can never change when somebody gets a charge. Otherwise, you change what the element is. So everybody has their own unique atomic numbers, so you can never change protons. And since neutrons have no charge, it has to be the electrons, really, the only thing that affects whether or not something has a charge. So in this case, we would actually have, in terms of electrons, 10 electrons. Yeah. That gives us 10 negatives and 3 positives, leaves us a -3 left over. That is where we get basically our charge from, is the difference in the protons and the electrons in this particular case. Right, like that. So this is known as an anion. And an anion is something that actually gains electrons from its neutral self. If we look at the one with a charge, that is 10 electrons. The one with no charge has 7 electrons. It has gained electrons. That is essentially what the negative means. If you see a negative charge, it has gained electrons. The actual number is how many electrons it gained. So originally it has 7, it has a -3 charge, so now it has 10 electrons. So an easy way to know is negative add, and 3, you could add it to the atomic number and it'll give you the proper number of electrons in that particular case. Is one way you could do that. Now, if we look at iron, for example, and we lay up iron here with a +2 charge, and we'll use the same numbers. Once again, our number of protons here is going to be 26. Once again, our number of neutrons will still be 30, doing that calculation. Again, here it is the electrons that affect the charge. And in this case, we will actually end up with 24 electrons. 26 positives and 24 negatives leaves me a net of a +2 left over, which once again is where the charge comes from. The result of this is somebody that has a positive charge, that's a cation, and it's resulting from a loss. They actually lose electrons in this case. And again, if you look at the difference between the neutral guy, which is 26 electrons, and the one with the charge is 24 electrons, it has less electrons, the one with the charge. Same idea here. If you see a positive charge, that means it has lost electrons, and the number is how many electrons it has lost from the neutral one. In this case, you could actually subtract. From the atomic number here, the 2, and you'll get the right number of electrons. So things that have charges, the only thing that changes are electrons. And again, positive gain, negative lose. I said that backwards. Try that again. Positive lose and negative gain. That's the way to do that here. So once you try this one, let's do and let's do numbers of protons, electrons, and neutrons. Okay, so let's take a look. So we'll start with our atomic number, which is on the bottom. So that's going to give us, in terms of protons here, 28. We have a +4 charge, so the plus means it has lost electrons, and it actually has lost 4 electrons from the neutral atom, which means we actually will only have 24 electrons. Again, you can take 28 minus 4, and I'll give you that number. That leaves us a net of +4 left over, which again is where our charge comes from. And our number of neutrons in this case will be 60 minus 28. Again, mass number, top number minus the bottom number, and 32, I think, in that case. Yeah. Any questions on that one there? I mean, here, again, we'll start with our atomic number, which is 34. So we got 34 positives. Here we do have a -2 charge. So the negative means that it has gained electrons, and the number of electrons it's gained is 2. And really, we could just add it to our protons in this case, gives us 36 electrons. Again, 34 positives, 36 negatives, leaves us a net -2 left over, again, which is the charge. Our number of neutrons, 80 minus 34, mass number minus atomic number. So that's like a 6, it's like a 46, I think. Hold on a second. Any questions on any of those with charges? So again, just electrons change in this case. Question on isotopes or any of those things? So as I mentioned before, the chemical properties really of elements are determined by protons and electrons in the atom. The neutrons really don't take part in normal chemical reactions, which is really good because that means a lot of isotopes will basically do the same chemistry as other isotopes of that element. So a lot of isotopes are radioactive, for example. So you could actually use that radioactivity to your benefit if you're doing some type of research and maybe you're interested in an element wherever it may end up in a process. You can use like a radioactive isotope of that element, and you can really follow, for example, the radioactivity throughout the process, and you'll know exactly where sort of everybody ends up based on where the radioactivity ends up. It's a very common sort of technique used in research labs. The next thing we're going to talk about is actually the periodic table. So let's talk about it here. The periodic table is an arrangement of elements. It gives obviously a good piece of information about a lot of things. So let's take a look at some of the parts of it. First off, when we look at the periodic table and we go up and down in the periodic table, that is what is referred to as a group, or if you're really old like me, a family, but most people don't even call it a family anymore. Most people roll with groups. And when we look at the periodic table, there's actually a lot of different numbering that you will sometimes see, as we can kind of see on this periodic table. There's just a straight, for example, 1 through 18 type numbering. There's also what is sometimes referred to as the A numbering or the representative numbering. And on some periodic tables, which you don't have over here, you also sometimes see B numbering happening in sort of this range as well. So there's a lot of different sort of numbering of groups. Now, for us and pretty much all chemistry classes you ever take, we roll with the A numbering. And the A numbering is actually group 1 is here. And by the way, group 1, as we'll talk about, actually starts with lithium, not hydrogen, even though it's hanging out right there on top of group 1. But group 1 actually starts with lithium. Right next door is group number 2. We actually skipped the middle, and this would be group 3, group 4, group 5, group 6, group 7, and group number 8. So that is the numbering that we go with, and pretty much all chemistry classes you take use that representative numbering. And technically it is group 1A, 2A, 3A, 4A, but most people don't actually use the A when they say it. They just kind of go group 1, group 2, and stuff like that. It's sort of assumed that they're talking about the A numbering and that sort of situation. We also have periods, and these are rows on the periodic table. These are the guys that head in this direction across the periodic table. And there's actually 7 periods. That's like period 1, 2, 3. Then we got like 4, 5, 6, and 7. So we got periods 1 through 7 going left to right on the periodic table. We also have talked about this previously, as we just did. Our numbers up on top of the symbols are our atomic number, which again is our number of protons, as we've been talking about as well. So groups up and down, periods kind of left to right on the periodic table. And obviously that number above the symbol typically is the atomic number. Now, the periodic table is broken up into really 3 sort of categories. There are metals, there are nonmetals, and there are what are referred to as metalloids, or semi-metals. On most periodic tables, you could kind of see this like staircase deal happening. And where that staircase is actually where our metalloids are. And really, kind of to the left of that staircase is where we find metals. Upper kind of right is where we find non-metals in most cases of that staircase. Now, a metal is a good conductor of heat and electricity. It's also malleable. You can hammer it into sheets. You can pull them into wires. They typically have a shiny appearance. Most metals are solids at room temperature. The one exception would be mercury. Mercury is actually a liquid at room temperature. And that's why a lot of times on periodic tables, if you look at it, mercury Hg, a lot of times is a different color, the sort of lettering of it and color of it. It's usually blue a lot of times. They'll kind of distinguish that. Now, this is also why, for example, I said earlier that in group 1, hydrogen is not part of group 1 because this is hydrogen right here. Hydrogen is actually a non-metal, yeah? So even though it's hanging out over here with lithium, which is a metal, it's over there for a lot of reasons because it shares similar properties. It kind of acts almost like a group 1 metal, but it is technically a non-metal. And again, why it's not really part of group 1, even though it's over there. Years ago, in a lot of periodic tables, they would actually throw hydrogen on both sides in some cases. You see it actually on both sides of the periodic table. Now, nonmetals pretty much have the opposite sort of characteristics of metals. They're usually bad conductors of heat and electricity. They have a more variety of a sort of state than metals. They're also dull, brittle, and insulators. Things like nitrogen, oxygen, chlorine, those are gases. Things like bromine are liquids. Carbon, sulfur are solids. These are also the nonmetals where we have those elements that come as diatomic molecules, like our H2, N2, O2, F2, Cl2, Br2, I2. So remember all these guys that are our diatomic molecules, which are also elements, are these nonmetals. And again, a lot of them are gases, so you got a lot of gases happening there through those guys as well. Now, our metalloids, which are also sometimes referred to as semi-metals, is really that staircase that comes down, sort of an overlap. Some books will also include boron as part of it sometimes, but we have sort of our staircase that comes down, and the metalloids are semi-metals. If you just think about sort of their location, to the left are metals, to the right are non-metals. So what these guys sort of have is, if you want to think about it, sort of a transitioning point between metals and non-metals. So the metalloids actually have properties that fall really on both sides of the staircase. The same metalloid will have some properties that are very similar to what you find in metals, and that same element will have some properties that are very similar to what you find in non-metals. So they kind of are like a crossover sort of elements, semiconductors and stuff like that in that sort of region. Again, they have properties similar to metals and also non-metals in that region. Couple other important things. Some of the groups on the periodic table do have special names that you need to be aware of. So starting over here in group 1, those are the alkali metals. By the way, once again, that starts with lithium. Hydrogen is not a part of the alkali metals because, again, hydrogen is a non-metal. So starting with lithium, right next door in group number 2, that is our alkaline earth metals. So our alkaline earth metals is group 2, beryllium, magnesium, calcium, and so forth. By the way, pretty much alkaline means basic. And group 1 and group 2 on the periodic table is where a lot of our strong bases come from. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. Pretty much if you hook up an OH with those guys, you get a really, really strong base in a lot of cases. Coming over to group 7 over here. These are our halogens. Those are our fluorine, chlorine, bromine, iodide, right? All of our diatomic guys happening. And right next door to it, as we'll talk about, are group number 8, and those are the noble gases. Noble gases are, as we will talk about here in just a second, are chemically inert. That means that they are unreactive. They are extremely stable. And as we'll talk about when we talk about bonding, that is pretty much the goal of all bonding, is for everybody basically to achieve the same electron configuration as the noble gases, because they're really, really stable. So that's really the purpose of bonding, is to sort of end up like a noble gas because they're really, really stable. So our halogens, just a little bit more in those guys. Again, there are a lot of gases and liquids. And again, we see very reactive metals. They actually will form acids like hydrochloric acid, hydrofluoric acid, hydrobromic acid, hydroiodic acid with all those halogens. But again, a lot of them are gases, as you can see, yellow, green, and then some purple solid that comes up there with iodine. Our noble gases, as I mentioned, there in group 8, also sometimes called rare gases. Very rarely they do nowadays call that. The two rows that are on the bottom here, these are the lanthanides and actinides series. They are set on the bottom, so it doesn't make your periodic table giant. But if you follow the actual numbering on the periodic table in terms of the atomic number, that's 57 and that's 72. Right here is 58, and that's 89 and 104, and right here is 90. So these two rows actually go right there on your periodic table. And again, they typically don't do that, put it there, because it will make the periodic table really, really long. And if you want to see that, the only place I've ever seen it is actually like next door in that room. If you look on the wall, it takes up the whole wall because it spreads the periodic table all across the entire wall because they put those two rows in the spot where it goes. Now, between group number 3 and group number 2, go right about there ish. Those are our transition metals. So one of the important things about transition metals that we'll talk about, for example, when we get to sort of naming officially, is transition metals typically have the ability to make a variable type of charge. So for example, copper in some cases can make a +1 charge or a +2 charge. Iron can make a +2 or +3 charge. So those metals have the ability, most of them, to make variable types of charges depending on sort of who they hook up with along the way. That's also why these two bottom rows are also sometimes referred to as inner transition metals, because technically speaking, that's kind of where they go in the middle there of the transition metals as well. By the way, they're called lanthanides and actinides because those are the two elements on the periodic table that they follow, basically. Now, the characteristic shape of the periodic table puts elements that have similar physical and chemical properties near each other. So things in the same group, obviously, a lot of times will have similar sort of properties. Even things kind of near each other in the same row will have similar properties. As you move from left to right on the periodic table, you're becoming from a more sort of metal to a more non-metal situation. Any question on the periodic table? So let's talk a little bit about noble gases here as well before we move on. We have also some noble metals, gold, platinum. They are also considered noble metals as they are very unreactive. And obviously our group 8 is our noble gases. So sometimes people refer to noble metals. And again, that's your kind of gold and platinum sort of metals, very, very unreactive as well. Noble gases, as I mentioned before, they're actually what are referred to as being monoatomic, which means they actually come as ones. So unlike like hydrogen gas, oxygen gas, nitrogen gas that come as twos, the halogens basically come as ones. A lot of them are colorless gases at room temperature. Again, very non-reactive and kind of the goal for everybody else to become like in terms of their electrons. And obviously, we've talked about our diatomic molecules there. And again, these are some of our non-metals, obviously, our diatomic molecules. Now, the structures of solids are really different. For example, when we talk a little bit about solids, there's different types of solids, but you can have uh, basically different forms of the same element. And when you have different forms of the same element, those are what are known as allotropes. And allotropes are these different forms. So, for example, if we took something like our nonmetal carbon, there are a few different types. You could have diamonds, you could have graphite, and you could have fullerenes. which are basically really long amounts, are a lot of carbons together, like 30 or more carbons all together. Kind of visually, if you want to think about what that looks like, it's kind of like a soccer ball kind of shape, basically, is what it looks like, 30 sort of or more carbons coming together. So the idea here is diamonds and graphite are essentially carbon, just cost more depending on the arrangement of those carbons. So you get more of the diamond arrangement here is going to cost you a lot more than, say, pencils. But in, say, the graphite arrangement, the carbons are actually arranged in sort of sheets of carbons, and that's what makes graphite. Again, you get a different sort of arrangement of those carbons, which gives you diamonds. And like I said before, kind of like a soccer ball sort of arrangement of all the carbons is what those fullerenes look like, 30 or more. So we talked about ions, and again, we'll talk a little bit more about these ions, and we'll get more into it when we get into really naming a little bit more. But an ion, as I mentioned, is anything that has a charge. And as we talked about, we have cations, which are positively charged, and we have anions, which are negatively charged. As we just talked about, basically that results from, in terms of the cation, somebody losing electrons. So for example, if we took sodium, when it loses an electron, will lose 1 electron. Neutral sodium has 11 electrons. So when it loses 1 electron, this guy will actually have 10 electrons. We could actually represent sodium losing its electron in an equation. We could take our sodium with no charge. It's going to make sodium with a charge, and the electron is being given off. The electron is on the product side of the arrow, which is the right-hand side of the arrow. And when you see an electron on the right-hand side of the arrow, that indicates that it's being lost or being given off in that process. Same thing if we look at magnesium. Magnesium here with no charge has 12 electrons. Magnesium with a +2 charge means it has lost 2 electrons. It will only have 10 electrons in this case. We could also represent that in equation form by taking magnesium with no charge. The magnesium forms a +2 charge and gives off 2 electrons. Once again, on the product side, we see our electrons being given off, which indicates that that is going to make a cation, and that's the way you can represent it sort of in equation form. Any questions on that? And obviously our aluminum here as well. Now, when we have basic ions, the way that we name basic ions is we simply just use the whole name for the cation. So we use the whole name of the metal pretty much. So if we had our Na+ ion, this would be known as the sodium ion. If I had my Mg2+ ion, this would be known as the magnesium ion. And if I had my Al3+ ion here, this would be the aluminum ion. We basically just use the whole name of the metal or the positively charged ion, and we put ion at the end because it does have a charge. Now, when we write the formula for the ion by itself, they should have the charges. So they need to have the charges if you're writing the formula for the ion. If you do not write the charges, you basically have this guy, which is just sodium metal. It is not an ion. So if you do not include the charges, if you're writing the formula for something that is a cation or anion, then it is not an ion. It's just like the metal by itself, for example, and it would not be considered an ion. So that's really important. Sometimes when people go write formulas for ions, they kind of leave the positive charge off or the negative charge off. You have to include that. Any questions on that there? Now, an anion, on the other hand, like we talked about, is when we gain electrons. We also can represent that in an equation form. So if we take chlorine that is neutral, it would have 17 electrons. Chlorine, when it gains a charge, will be a -1 charge, and that will be 18 electrons. It has one more electron sort of happening. And we could represent that in equation form by taking the chlorine plus the electron, gives us now the chlorine with a -1 charge. The electron here is on the reactant side. And that is how you would indicate it in sort of equation form, the formation of this anion, which is negatively charged. Same thing here with the fluorine. Fluorine plus an electron will give us our fluoride sort of guy. Now, how do we name our negatively charged anions? Anions are named a little bit different. Basic anions, you take the root of the nonmetal name and you drop the last part of it and you replace it with IDE. So instead of chlorine, Cl minus will become the chloride ion. Instead of bromine, Br minus would become the bromide ion. Or even oxygen. Instead of oxygen, oxygen with a -2 charge would be known as the oxide ion. So sometimes you take a little bit more of the name off, but they typically all end with a IDE at the end of it. Once again, same idea. If you're going to write the formula for the anions, you do need the charge. Again, same sort of idea. If you do not write the charge, then it's basically just sort of the element by itself. It doesn't have a charge or anything associated with it. Ions are never formed by changing, again, the number of protons as we talked about. It is just the electrons, again, as we did earlier, that affect the charge. Any questions on that there? Now, when we look at the periodic table, there are certain things on the periodic table that will form fixed charges. Now, just a reminder that things on the periodic table do not have charges if they are by themselves, uncombined, just hanging out by themselves. Things only get charges in sort of a situation when like metals and nonmetals get together. That's basically where they get their charges from. Other than that, they really don't have charges until they kind of hook up. So if you took just sodium metal off the periodic table, it has no charge. But if you take the sodium and the chlorine and put it together, then it will gain a charge at that point. Things in group 1 will typically make a +1 charge. Things in group 2 will make a +2 charge. We skip, and really for the most part, it's aluminum will make a +3 charge. Then right around here is that staircase that kind of comes down. So the nonmetals above the staircase, starting at group 5, will actually make a -3, -2, and -1. So it's kind of like 1, 2, 3, skip, -3, -2, -1, and go that way. Now, these guys, no matter what the situation is, will always form those charges. So you'll never find, for example, a sodium that has a +2 charge, +3 charge. It's always going to lock into only a +1 charge, no matter what the situation is. Same thing with the, say, sulfur, for example, in an ionic compound. It will only make a -2 charge. Transition metals, as it says, has a variable type of charges, which means they can make different types of charges. There are actually 3 exceptions that may have fixed charges, and that is zinc and cadmium, which are transition metals. When they make a charge, it is always +2. And if you hang a left at cadmium, where silver is, that guy is always +1. So these guys will always make those sort of fixed charges. So these guys always will have those fixed charges, no matter what the situation is. Any questions on that? That's really good to understand when we get into naming as well. Now,